Let's talk about angular frequency. Now, the symbol we use is the omega. We use the lowercase omega. The uppercase, we use that for resistance or ohms. And the formula you use is omega is equal to 2 pi over capital T, the period. The period is the time it takes to go around the circle once, or one complete sine wave. Now this 2 pi up here, we use radians instead of degrees. So instead of using 360 degrees, we use 2 pi. Now, a radian is equal to, if you take the diameter of this, or the radius of the circle, and we plot that along the circumference, say from point A to point B, this angle that it makes, this angle theta, that's 1 radian. Happens to be 57.29 degrees, but that's 1 radian. In a circle, there's 2 pi radian. There's 6.28 radians in a circle, okay? This pi, we get that by taking the diameter of the circle and divide it into circumference. And if you do that on any circle, you're going to get 3.14, and it keeps going on forever. And we know the diameter is 2 radiuses, so we divide 2r into the circumference to get our pi, 3.14. And the circumference is equal to 2 pi times r. So, and now 2 pi is going to be 6.28 times the radius. So, and this happens to be the same distance as a radius. So there's going to be 2 pi radius in a circle. So 6.28 radians in one circle. Okay. Now, to find a frequency, we just take the time, this period, and we divide that into 1. So if it takes 1 second to get around, we divide that into 1. That's 1 cycle per second, or 1 hertz. If it's 0.5 seconds, then it's going to go around twice in 1 second. So that's going to be 2 cycles per second, or 2 hertz. Okay. And we usually rewrite it omega as 2 pi times the frequency, because we usually know the frequency, we don't not always know the time. Now, we use that in some common formulas like the capacitive reactance. We have 1 over omega c, and inductive reactance is omega times the inductance times L. So instead of writing 2 pi f times c, we can just write it this way. And this is where most commonly you're going to see this omega symbol here. Now, how do we get this sine wave out of this circle here? So down here we have a generator, and we have north and south pole on a magnet, and we're going to spin this magnet around. We're going to spin it counterclockwise. And right now, in this position, the voltage is going to be 0, because there's no lines of force crossing this coil up here. As this north pole rises up to the coil here, the voltage is going to increase. As it passes over the top, it's going to peak out up here at 90 degrees here, or pi divided by 2. And then as it leaves, the voltage is going to drop off. So it comes back around this way. This is going to be 0 again, and that's going to be pi. That's halfway around the circle. And then this south pole is going to come up, and the voltage is going to rise up until it peaks out when the south pole crosses the coil here, down here. Of course, the electrons are flowing in the opposite direction, coming down this way. And as it leaves, the voltage drops back off, and it winds up like this again at 0, back in the same spot. So that's how we get our sine wave out of this rotating magnetic field here. Now, there's the difference between angular velocity and angular frequency. So angular velocity is the angular change per second. So it's a change in the angle theta divided by the change in time. And it's in radians per second. And up here, this is radians per second also. But it's the change in theta over the change in time. Okay. Now, angular velocity changes in time. Angular frequency does not change in time. Okay. Now, we use the same symbol, the lowercase omega, for angular velocity and for angular frequency. Now, but for us, the confusing part is that if we have a constant speed around our uniformly rotating disk here, or the magnet's rotating around uniformly, which it does for us, at that, in this case, your angular frequency and angular velocity will be the same thing. But a lot of times, say in a pendulum or something, angular velocity and angular frequency won't be the same. But in our case, angular velocity and angular frequency will be the same. We use the same omega symbol, but they are different. But for us, it works out to be the same. So I think that's angular frequency. Thank you.